second lecture of the series. And Sergei, please, the floor is yours.
Yeah. Okay. So actually, my career was mainly devoted to theoretical particle physics, HEPTH, but it was not deeply connected with phenomenology. But in more recent years, I was starting paying attention to the where actually these very high energies take place, and what could be the highest energies which were available in our universe. And this naturally leads to inflation, and you will see during this talk why cosmological inflation is a very natural and perhaps the top arena for high energy physics, very high energy physics. Okay, so I assume that you attended my lecture yesterday, which was a kind of basis for the, what I'm going to talk next. So cosmological inflation in the very early universe, yeah, it's well before Big Bang nuclear synthesis, well before any astrophysical objects creation, yeah, well before even particle creation. But after, and well after the quantum birth of the universe. So I will talk about the general picture on Friday, February 20 here. Just want to tell you that the basic scenario is universe was born quantum, then space-time was created, then inflation happened, and then particle creation. So this is a series of events, and we want to know, of course, details, and we want to know, not just get it from pure thought. You can imagine huge number of theoretical models. We want to see what nature tells us, and what are, so we need the observations and signals, and the deepest signals we have so far is from inflation on cosmic microwave background radiation. Okay, so again, I always start from some textbook to get a connection to what you know, and then I build up, preferably to the state of the art. So, what is inflation? So inflation originally was a proposal, which is called, it's not specific, yeah, it's just an idea or cosmological paradigm, as it's called, about the existence of extra phase in addition to Einstein-Friedman cosmology, actually preceding it, which in the very early universe, so just this incredible time, before radiation domination area. So it can be seen as a kind of dark energy too, because it assumes the accelerated universe, but it has to stop very quickly. So the difference with dark energy, current dark energy, that this has to have what's called graceful exit, which will connect to the low energy physics, and it will have to stop quickly. Okay? So it was purely theoretical. At that time, I was just in the same place where Starobinsky, Linda were, Moscow. I was a graduate student at that time in the Ginsburg lab. And at that time, it was purely theoretical considerations. Even though very convincing, as I said, Einstein-Friedman cosmology had the internal problems, and inflation was a recipe to get rid of them. But now we have significant observational evidence, and actually what's called precision cosmology, due to precision observations of CMB. So the metric, this means that the metric which describes actually the universe, not only just Friedman metric, it has Friedman metric plus perturbations. So we have to concentrate on perturbations because these perturbations are imprinted in the picture of cosmic microwave background radiation, and they are measurable. Okay, good. So first, my plan for today is first to give you some physics qualitatively, and then describe it quantitatively in a particular setup. Okay, so as I mentioned, the major motivation for cosmological inflation, not historically, but today, is that it can provide the seeds of structure formation. And the idea is that inflation works like a huge amplifier of quantum fluctuations, which are always present, we know from quantum field theory, and amplifies to the macroscopic fluctuations that becomes seeds of structure formation in the universe. So originally, these techniques were quite complicated. So you can go to this, for example, this, which was systematic, okay, but rather complicated, because metric is a gauge field. You have to deal with the curvature fluctuations, and this is rather technical. But more recently, or later, it was significantly simplified. That's why I recommended you yesterday the book of Liss and Liddell, where they put it in a so simple way that practically anybody who is familiar with general relativity can do it. So this was explosion of paper then about that. Okay, so I will show you how it works in a simple way. Good. So first of all, I just remind you, not remind you, but just tell you how assuming inflation solves the old problems of the standard cosmology. So as I mentioned, what are these problems? It's a dependence upon initial conditions, heavy dependence upon initial conditions, which makes our universe, Einstein-Friedman, highly unlikely. Second is horizon flatness problem. Why universe is empty, which flat, which means why omega is 1, which means that total density is a critical density. Third problem is a horizon problem, which is even more severe from the point of view of physics, but I just want to give you the key points, how these problems are solved. So problems of initial condition is basically solved by demanding that the inflationary solution, namely the evolution of the universe, has to be not just any solution of differential equations, which depends upon initial conditions, but a special solution, which doesn't depend upon initial conditions. And in a theory of partial differential equation, it is known as attractor solutions. These are special solutions to differential equations, which are essentially doesn't matter, independent upon initial conditions. So the inflation solution has to be attractor solution. This is a heavy mathematical demand, which is sometimes ignored by many people, but it is experts understand it very well. Actually, I will show you the solutions. That's why it's just a demand. To reduce the problem of initial conditions, inflation should be attractor solution to the equations of motion. This is just a general idea. A realization will come next. Another question is how we solve the horizon problem. Actually, this, by the way, this demand of attractor solution will also lead to explanation why omega is 1. Namely, the attractor will lead to omega 1. And this is a point. This is also a physically important point, because if the solution is attractor, then inflation basically erases information from the past. Therefore, there is no way to have observable information before inflation. So you can talk about it any time, you can propose any suggestion, but it is not verifiable, not questionable, not measurable. So therefore, from my point of view, it is not physics. Physics is measurable and verifiable by experiment. This is an important point. Qualitatively again, yeah. First, second, how it solves the horizon problem. Horizon problem is a problem that apparently naively causally disconnected part of the universe have the same CMB pattern. So they have to be connected somehow before. when during inflation. So how it is solved? It is solved very simple way, namely, what is the causally connected radius? Which relates events which are causally connected. It is just h minus 1 over a. It follows from the field theory. So when you consider the derivative of this Hubble radius, which specify causally connected part of the universe, from these conditions you get this condition. This means on the one side we have the expansion, very fast expansion due to the cosmic factor, but on the other side, which is equivalent, we have a reduction of the causally connected part. This is the main point of inflation. So if it is squeezing, then it can be easily mixed, like when you when you put sugar into the tea. So the more better definition of inflation, not like this, which is usually quoted, but like this, which means inflation in a zooming on a tiny part of the universe, and this explains physics of inflation. This is how it qualitatively solves the problem. Okay, so this is usually put in textbook or reviews in this graph. So you see scalar factor is increasing, but the during inflation, Hubble radius is decreasing. So this is the meaning of the how it solves in principle the horizon problem. Okay, so in order to go to more details, I have to develop some notation. Okay, so we have to deal with big numbers. For example, change the scale factor in the metric from end to the initial to the final. So these are big numbers. So usually one takes a log of this, and instead of timing, one uses so-called E-fold number, which is defined like this. This just follows from the fact that h is a dot over a. So this is just a definition of this number, which has no dimension. So this determines the duration of anything, in particular duration of inflation should be from various sources around 50, 60 E-folds. Okay, good. So the idea is to now to connect this at this era of to the before radiation domination, and then also you have to provide a detailed mechanism of inflation, because if you don't provide detailed mechanism of inflation, you cannot really get many things. You will be stuck just at the level of blah blah blah. So it's actually a non-trivial problem, and you will see how it was resolved over the last 40 years. Okay, so just as a warm-up, let us consider just a cosmological constant, so or roughly constant positive potential. Okay, so from the Raychaudhuri equation we saw that the pressure has to be effectively negative, and this can be easily realized by cosmological constant. So if you solve the equation, the Friedmann equation, which is Einstein equation, yes, with such a cosmological constant, you get this solution, and you get omega common to 1. So this means that if you want to reach omega 1, you should have approximately flat potential. Approximately flat potential, but it doesn't solve the problem at all, because this is an eternal inflation. It comes forever. You have to stop it quickly. And this is non-trivial even from a mathematical point of view. It took more than 15, 20 years to solve such a problem. Okay. So this means since you exhausted, so to say, resources, if you have only Einstein gravity and cosmological constant, you have to add something. You have to have a driver of inflation, So basically you have to have a time-dependent cosmological constant, and time-dependent cosmological constant is a scalar, and we call this scalar, so you need a scalar that will drive inflation. So this means you have to extend Einstein action with a minimally coupled scalar field, and this scalar field, which is called inflaton, is supposed to drive inflation, and you have to find the solutions which are attractor, which give exit, which agree with CMB, and so far, so on. Yes. Yes.
What is its statistics? Is it fermionic? Is it
But no,
bosonic?
scalar.
It's a scalar.
Spin zero.
It's a simple scale. Okay.
Simple.
It's a scalar.
Yeah, you cannot
Okay.
do it with fermions. No.
Okay. Okay. It's spin zero.
Because it's spin
And-
zero.
Okay. And does it have mass?
Yeah, I will come to that.
Oh, okay.
I will come to all details. Please,
Oh,
you
okay.
get ahead
Sorry.
of me. Yeah. Of course it does. Without massless scalar, cannot do it. I'm just telling you what is required, and then I come to realization, which is really hard stuff, important stuff. Okay, good. So let me just describe what you just asked, yeah, in more details. So this means we just add the minimally coupled canonical, yeah, scalar field. So this is a standard Lagrangian for scalar field. So this is kinetic term and this is a potential term. Potential term we don't know, we have to find. Yeah, and once you have this Lagrangian, you can calculate energy momentum tensor, which is the right-hand side contribution to the Einstein equation. So it is given here. Yeah, and if you go to the comoving frame like this, you get that C00 component, of course, is this, and this is rho. Yeah, this is C equal 1, yeah, mc squared, E equal mc squared. So this is energy density, or Hamiltonian if you want. We ignore x dependence of phi. We keep only time dependence because x dependence of phi is irrelevant for the Euler universe. Okay, so we take phi only as a function of t. Good, and Tij determines the pressure. Yeah, this is a Pascal law. Pressure is in all directions in space is the same. So pressure is this one. So you can see that this is energy density has to be non-negative, and this is pressure has to be negative. So it can be easily negative if we take if this term positive and dominates over kinetic term. Yeah. Good. So we can easily make this negative because this has to be negative. So this means V has to be more than this. So if we demand this condition, we have the negative pressure enough for the dark energy, but we will do more. We will do actually this condition, which is called slow roll, because I mentioned to you that we need kind of sufficiently flat potential. Sufficient flat potential implies slow roll. So just imagine classical mechanics running the point-like mass around the potential, okay? So this means this is called slow roll condition. This is a standard demand for inflation because this immediately solves the problems with negative pressure and so on. So we just need only scalar field, yeah, which is driver of inflation. Or we can also write down the Friedman equation. So you can forget about this term. You can forget even about this term. So h squared directly related to the potential. Okay, so this means the potential we have in mind should look like this. Okay, this is at some energy. This is the inflationary phase. Yeah. Inflaton rolling slowly around this plateau, then it drops into the minimum, start oscillating, and in the inflationary, in the expanding universe, this leads to the particle production. This is a physical picture in mind. Good. You can also write down the equations of motion for the inflaton, which is a standard Klein-Gordon, okay, in gravity. But if you put Friedman metric, you will get this with time-dependent phi. So you see, this is the usual equation which you are quite familiar with the classical mechanics. So you see that H plays a role of friction. H is positive. It is an expanding universe. So this means dynamics of inflaton is governed by potential. Prime means derivative, okay? And you have a friction term. So in a slow roll approximation, you can ignore this term, so you'll be just second and third. This is the physics we have in mind. Question is how to get it in details. This will be next.
So why exactly you need slow roll?
Yeah, you need slow roll just to guarantee that first of all, you have the negative pressure, and second, you have enough duration of inflation. Because if this means if you have too short duration, you cannot reproduce our universe. It should be around 50-60 fold. Okay, so so this is slow roll conditions. By the way, this was all written in paper of Starobinsky, 78. So I'm talking about pretty old stuff, but at that time, there were very few people in the world who were studying such things. Okay, so let me skip it. Maybe before I just a moment. The central part later in our discussion will be played by the spectrum of perturbations. And spectrum of perturbations is essentially the, it's a two-point correlator in a Fourier transform. So this determines the spectrum, also in condensed matter, in physics. So this spectrum is determined by the potential. And there is a formula for such spectrums. If you have a metric, in space, you can decompose it into the trace part and the traceless part responsible for scalar perturbations, and traceless part responsible for tensor perturbations, which are gravitational wave, primordial gravity waves. So you will get two spectra, one for scalar perturbation, one for the tensor perturbations. And what is measured by satellites today are certain tilts or certain indices of perturbations, so kind of derivatives at a particular scale. So, for example, this is called the scalar tilt, which is a derivative of the scalar k, represents energy scale. And so this is exactly what is measured by astronomers and satellites. And there is a similar formula for the tensor perturbation. Usually they say they consider the ratio of tensor perturbations with respect to scalar perturbations called the tensor to scalar ratio. This is also one of the main targets of the observational cosmology today. Okay, so these formulas are derivable in the good books and in reviews. I will skip this. Okay, so how this can be greatly simplified. It was greatly simplified by Liddell and Lees in the slow roll approximations, because in slow roll approximations you have just Friedmann equation and the Klein-Gordon equation approximately, and you can define what is called slow roll parameters, which are measuring how slow roll is. It has to be very much less than 1 in absolute value. So they are called epsilon parameter and eta parameter. So this is the first derivative potential. This is the second derivative potential. So if they are small, then you have a relatively flat potential. So usually you can control easily. Somebody gives you potential, you check slow roll parameters. If they are not less than 1, then forget about it. If they are less than 1, well, let's consider. Yeah? So this is the basic idea. So this means that from my point of view, inflationary solution should be like a half of solenoid. Yeah, so doesn't matter which initial conditions you begin, it goes to the particular pattern. Yeah, and so this basically erases memory what was before. This is the idea. This is ideas, and realizations will go in a moment. Okay, so and perhaps again I want to emphasize that from this point of view, physically, you can think about inflation as the most natural accelerator in nature. You cannot compete with that because you will see the energies are 10 orders of magnitude higher than the LHC. Yeah, so even if you build FCC, it will be still uncomparable to the inflation, which acts as a huge accelerator. Okay, so what astronomy tells us, for example, astronomy tells us that the spectrum of CMB is proportional to energy times energy scale times n minus 1, where n is just a scalar tilt, okay? And this was observed with high precision, and this precision is increasing with time. I just referring to the very old observation, but this was a spectrum which is known in literature as the Harritz-Zeldovich spectrum. It was proposed many years ago. It is indeed true. Moreover, this spectrum is almost conformally flat. You see n is pretty close to 1, but it is not 1. Yeah, so this is this famous statement about the CMB background. Okay, so just before I go to details, I want to emphasize quantum origin of these fluctuations, which we observe in macroscopic level. Well, this is just exercise from quantum field theory. If you write down, if you consider inflaton as a sum of a classical field, which satisfies classical equations of motion and quantum correction, small one, yeah, then you write the equation for classically, you vary it with respect to phi, you get linear equation for delta phi with in phi classical background, you decompose it in Fourier series and then into the plus and minus modes, like you taking care of the expansion of the universe, then you quantize canonically and you consider delta phi squared, which is quantum mechanics, like delta x squared average, yeah, and the result is that it's basically proportional to the h. So it means if you have no expansion, then this quantum fluctuation have they're basically virtual. You can forget about them or factorize them. But if the universe is expanding, this is real. It is non-zero. Okay, and this allows you to connect. Well, to connect. These fluctuations, which are macroscopic with a microscopic fluctuation, which shows the origin, quantum origin of this fluctuation. So even though they were born quantum, they can be seen as after inflation, or during inflation, as a fluctuation of the CMB. Good. So this is gives you connection to. Because to observations, because this can be is observable, for example, and this principle also observable. And I now go to the way how it is. Well, this maybe I skip. Maybe I should also mention. I promised you that you don't have to go into many details, because now this key. Cosmological tilts are simply related to the slow parameters. In particular, tilt of scalar perturbations is just a linear combination. In the first approximation with respect to slow parameters, and the tensor to scalar ratio is just 16 epsilon. So in most papers nowadays, people just skip all this stuff, use this formula, take their favorite potential, put epsilon eta, and try to satisfy these conditions. Of course, CMB is a rather small windows into the high energy fields, but it is a real window. So that's why this is an important source of information. Good. So now I want to tell you what is the connection with the observations in more details. Okay, so first of all, I need a formula for the power for the spectrum of perturbations. It usually measured at the horizon at any particular scale, horizon exit. So the formula is in the slower order approximation. Exact formula is not possible. Is written here, where prime is just derivative, and or it can be put also like this: v over epsilon. Remember, epsilon is v prime over v. Okay, so this means this is what measured, but it measured in particular range of scales. Okay, so since this is measured, for example, by Planck mission or satellite mission, we know the value of this. This is what WMAP measured and Planck mission confirmed. So this means this is a huge scale, okay? But it doesn't fix the potential, because it fixes only this combination, okay? So for example, you may put just a mass term, yeah, as a trial, as a potential. If you put a mass term, you will get a mass 10 to 13 GeV. That's why how you get the inflaton mass, 10 to 13 GeV, yeah? What is the Higgs mass? 125 GeV. Okay, this is very, very high energy physics. Okay, you ask about the mass, it gives you an idea. Okay, you can put also the conformal potential. Lambda has no dimension. Yeah? If you put such a potential, you will find lambda is too small. With such lambda, you cannot go really seriously, because it will be subject by any quantum correction. So this is not good. This means both this potential and this potential almost root out. Well, but why this root out is a tricky story. This one is not acceptable physically. Yes?
Well, I'm sorry, but I seem to have missed one thing. I understand that the inflaton is not the Higgs boson, of course. So they have, as you say, that
Naively not, yeah.
Yes, but if it has a mass at all, it means the Higgs mechanism must already be operating. Of course, that's where all mass in the universe comes from, the Higgs mechanism.
Well, it is just masses of standard model particles, not inflaton mass. Inflaton is not in standard model.
Okay, so you're saying the inflaton mass does not come from the Higgs mechanism?
Absolutely no. Higgs mass is needed to get masses, to bring masses to the W bosons and so on. So
Yes.
to bring the mass scale to the standard model.
Yeah.
Inflaton doesn't belong to standard model, it's beyond standard model elementary particles.
So it does not come from the Higgs mechanism. Where does it come
No.
from?
Well, just have to put it, this is my next slides.
Okay.
Sonky, you are following me very well, you're ahead of me, but you're precisely telling me where I have to go.
This is all assuming that this is an elementary particle, so it might not be an elementary particle.
Well,
So
we added scalar fields. A quantum excitation of scalar field is scalar quantum particles, okay? And if I just start making basic tests by putting some favorable, simplest potential, I discover that it has to be very heavy. Of course, Higgs mass also subject to renormalization, of course, yeah? So it can become heavy, but this is a more critical question. What I'm saying to do, from this point of view, it is absolutely disconnected from standard model at the moment. I have to describe CMB. How we come to standard model, I will come next, okay? But for the moment, it's completely disconnected with the standard model. Standard model doesn't have it, because it doesn't have gravity. Here, gravity plays a major role. If you add standard model, if you add minimally coupled standard model with gravity, you will never get it, because there is no such particle there. Higgs cannot, well, it can work at a certain extra assumptions, which is called Higgs inflation, maybe you heard. But this is okay. I can comment it at the end, but this is not relevant for. I will tell you also why it also doesn't work, if you are interested. So for the moment, I'm telling you what are the constraints. This is not arbitrary business, okay? We have this constraint, and it tells you that you have to deal with the very high energies. This is what my only message, which is far beyond standard model. So to make a connection 10 orders of magnitude, it is a daunting task in physics, you know, and this is, I prefer to skip at the beginning. No connection to standard model. We need inflaton, which is a driver of inflation. We forced to have it, and I want to fill the job first with inflation. Then question how is it connected to standard model. Okay, good. So, yeah, let's continue. This probably I will skip, because of course you can ask, oh, great, wait a minute, we have inflation, we have CMB, maybe we can reconstruct potential from the observations, from the power spectrum. Unfortunately, it doesn't work because the window is too short. So let me skip this. I will not do it. Good. So now let me describe you the current situation with in cosmology, in inflationary cosmology. So if you put here NS values, which are measure scalar perturbations, or density perturbation, or temperature perturbation, or you put here tensor perturbations, which are measured by tensor to scalar ratio, okay? Then what happens? What about NS? It was measured precisionally around 0.96, and it was even more and more missions coming after WMAP and confirm it, in Atacama telescope confirmed, South Pole confirmed, so no question about it. This is this. So these colors, I mean 1 sigma, 2 sigma, 3 sigma agreement, yeah? The R was not measured yet, but the bound, the experiments lower the bound all the time. So this is not the latest picture, for example. It was some time ago, a few years ago. Now the bound lies at 0.03. So it is here. So it's in all models, potentials, yeah, which are above this bound, ruled out. In particular, all potentials of power law, which you would naively try first, yeah, they all now above the bound. It was over the last years. So even harmonic oscillator m squared, phi squared is ruled out. Even phi 4 ruled out, and even phi p with any power is ruled out. So what to do? Of course, you can invent some very sophisticated potentials, but usually this is not a good idea because most of them have some other problems. Yeah, try simple. There should be good reasons in physics if something happened. So again, remember this number 0.032. Actually, it is here. So the current 1 sigma agreement is now just this. Just this. There was a question from you, I think, yesterday about grand unification. Yeah, I can comment about this now because this tensor to scalar ratio is directly related to the Hubble function. Hubble function measures the energy, relevant energy of inflation. So the current bound 0.03 goes to high inflation h to 14 GeV. This means that any mass beyond can never be produced, because this is the maximal energy in our universe which is available. So this means even though formally grand unification mathematically happens at 10 to 16, but the maximal energy in our universe, which can be relevant for particle production, is 10 to 14, 100 less. Therefore, grand unification never realized, and any particles beyond 10 to 14 never were produced. We already know it now because we have the bound on R, which means the bound on maximal energies in our universe for particle production. This is not written yet in the book because they were not written the books yet. Okay, this has very far-reaching consequences. Good. So let me just tell you that this model, which is on Linde model, was proposed in 1981, and it was a leading model of inflation for 40 years until 2014. Because it's simple, harmonic oscillator, that can be easy, yeah? Mass is 10 to 13 GeV, okay, fine. So if I put this model, so the mass we already get from actually it comes from the amplitude of CMB fluctuations from the formulas I gave above, 10 to 13. But then we have to calculate these two key indices, NS and R. I will, if you calculate NS in terms of E-folds, you get this famous formula. It is Mukhanov-Chibisov formula in the literature known. It is very nice because you see N is around 50, so you get NS precisely around observable value. Yeah, what can be simpler than this? And it's derivable from this model. That's how Mukhanov became famous. Huh? No, well, well, you calculate epsilon and eta as a derivatives, and then you put it in and express it in terms of NS, because NS related some integral, you have to have some numerics. It's not exact formula. There are higher order terms, but 1 over n squared, they're negligible. It's just a leading approximation. So this famous formula explains the scalar perturbations CMB, yeah? But if you look at the tensor perturbation or tensor to scalar ratio, it is just this. You see, 0.15. So 0.15 is the number that predicts, well, basically, by the way, you can also exclude n in terms of NS, put it here, yeah? So n is not well measurable, but you can make a direct relation in terms of NS. So you get this number. 12 years ago, Bicep 2 reported that they measured precisely this. So one of our colleagues from Bicep 2 went from, he's Chinese, went from South Pole to the home of Linde in California to congratulate him with a Nobel Prize before Nobel Committee decided. Okay, real story. Okay, Linde said, let's wait. After the next couple of years, it turns out that their measurement is incorrect. They didn't include into account dust effects. Some cables were broken, you know. Well, South Pole, you know, minus 50. So, and then there were papers. For example, one paper was 120 institutions in the world. I never saw paper with 120 institutions in the world that dismissed this result. But it was 1213. Now we have 1225. It's forgotten. And now we have that R is not 0.1. It is 0.03 maximum. Okay? I told you that the most important direct confirmation of inflation is measuring of R positive. We don't have it, but we have upper bound. So this upper bound is enough to rule out this model. Then you have to look for some sophisticated models. Okay, you can get it because, of course, you can develop more sophisticated potentials. But do you have better theoretical reasons to describe inflation, which turns out to be more sophisticated than naive harmonic oscillator? It doesn't have a plateau, yeah? Yeah, it does, and it is known as Starobinsky inflation. Now I'm going to show you this, why it works, and why it is much better than this, and agrees with observations. Well, it is Lightbird Corporation right now in the making. It will be next year. Then it's Simons Observatory, and there is a Atacama Cosmological Telescope, South Pole Telescope. There's a competition of at least 5 collaborations in the world. Main target is to measure R, because the R is a key issue. Of course, they can measure 10 to minus 3, which is precisely. You'll see what Starobinsky predicts, but if it is lower, you will have another technology. At 10 to minus 4, there is no technology. It will be next generation measurements. This is a key issue in cosmology today, measuring of R precisely. Okay, so now let me tell you something, how we can understand Starobinsky model. First of all, in the literature, they usually refer to his paper in 1980. It was proposed even before Linde. But Starobinsky is not good at writing understandable papers. You will get almost nothing from reading his 1980 paper. So I worked with him. He is a genius, but he is not good at presenting talks and writing review. He never wrote any reviews. So I was asked to prepare the modern account of Starobinsky inflation. It will appear, it is available in archive, but it will appear in the memorial volume for Starobinsky in July this year, which will be published by Springer. Basically, I will put it upside down. So what I'm talking about is not in the Starobinsky paper. Actually, he was interested in totally different things. Okay, so, but for that, I have to go a little bit different story, which is less familiar to particle physicists, but very familiar to those who do gravity, namely modified gravity. So in short, what is modified gravity? We know that Einstein-Hilbert action, which is just this, yeah, it is not ultimate, cannot be ultimate action. If you took a course of general relativity, you know that Einstein got this section by demanding Newtonian limit and general covariance, minimal way. But this section is not normalizable. So obviously it has to be corrected, yeah? It has to be different in a full theory. So it was only checked in a solar system where curvature is small. But if you talk about inflation, curvature is large. There is no reason to demand Newtonian limit there. For large curvature, it was never tested, Einstein action. Therefore, there is overwhelming evidence that it has to be corrected or modified. So if you stay within gravity and don't give up general covariance, you have to add to this section some high curvature terms. This is the only thing you can do with covariant derivatives and curvature, and it has to be scalar. Yeah. So, for example, but this is known as a modified gravity. There are thousands plus papers about it. But the problem is most of them have a serious flaw because most of them have ghosts. This is, if you heard about Ostrogradsky's theorem from 19th century, which basically tells you that whenever you have a high derivatives in the action, in general, you have a ghost. And we don't want ghosts. I personally also don't want to live with ghosts. So, but this is very serious abstraction or discrimination, because you have to feel, you have to choose such modification which doesn't have ghosts. It's one thing. Another issue is, so even before any physical application, you want to consider ghost-free action. For example, if you consider beyond R, next level is a quadratic gravity, quadratically generated gravity. Yeah? In quadratically generated gravity, there are only three possible terms: full curvature squared, Ricci squared, and scalar curvature squared. So the most general is a linear combination of them. However, you can kill one of them because there is so-called Gauss-Bonnet combination, which is a total derivative. Total derivative doesn't contribute to equation of motion. We are interested in equation of motion. So this means you can kill out of 3, 1. Another point is there is a linear combination of A mu squared and A squared, which is also total derivatives for the Friedman metric. So you can kill also A mu squared. So it remains only in A squared. And actually, if you now complement the investigation of ghost freedom, the only possible quadratically generated gravity is A squared with a positive term. So you have no choice but just to add only A squared with a positive coefficient. Just pure thought. This is known as Starobinsky model, and of course this is just a formal requirement. But what I'm now telling you that this is perfectly describes inflation, how it does. So this is, let us start from this. It doesn't exclude higher order terms, but I want to emphasize the importance of A squared term. So the only thing we can do, yeah, we add A squared, and this has higher dimension. Yeah, this has dimension 2. Okay, so this has dimension 4. So you have to put here some mass coefficient. Otherwise, dimension will not match. Let us call it M. Okay. In modern terms, this is sometimes called as a particular representative of FR gravity. And I want to emphasize, we consider this not a correction, but a full non-perturbative action. So, what is interesting about that? First, formal point, from the formal point of view. Okay, you put a Friedman metric, you write equation of motion, put a metric, yeah, and you get an equation for the scalar factor or for the Hubble function, which is this. This is known as the Starobinsky equation in the literature. This is a nonlinear ordinary differential equation of the second order. What is remarkable about this equation? It has an attractor solution. That's what the main discovery of Starobinsky in 1980. And it cannot be written explicitly. I just wrote it in terms of some expansion. So just concentrate on this first term. It doesn't depend upon initial condition. It's a special attractor solution. Good. So how in terms of slow row conditions, this is just this. So we have a situation. This gives us interesting picture. In the low curvature regime, you can ignore R squared, like our solar system. You have just Einstein action, and Einstein action is perfect for solar system gravity. We know it with a high precision, okay? But if we go to the high curvature regime, large R, then we can ignore Einstein-Hilbert term. Then the action becomes just integral over R squared. What is remarkable about this integral? R squared has dimension 4. If you integrate R squared over 4 dimensions, it has dimension 0. Therefore, effective coupling constant is dimensionless. This means it is scale invariant action. Scale invariant action, effectively, yeah? And this solution, it breaks scale invariance because it introduces a scale. So you have a spontaneous breaking of scale invariance. According to the field theory from textbook, you have to have number-Goldstone boson associated with such a spontaneous breaking. Okay, so you have to have a scalar field in addition to metric, yeah? And indeed, you can see it if you make a transformation from this action to the usual scalar field action in medium gravity. This is known as the Legendre-Wald transform. It's just a combination of Legendre transformation and Wald transform. So you can, through these redefinitions, just basically field redefinitions, you can rewrite this action into this form. This is just look like a miracle, but it is a literal, it is what's called example of dualities in this particular series. So the series with high derivatives, which is r plus r squared, is actually equivalent to the standard scalar tensor series, but it predicts the potential. Potential is predicted like this. So what is remarkable? You generate positive height of the potential, and you get the small exponential correction if phi is large enough. So this is called Starobinsky inflation. It's perfect for the inflation, for describing of inflation, which I just described. Okay, so this is a theoretical preparation. I didn't even put any observation here. Yeah, it is just a theoretical observation. But the key point is that we don't demand flatness of scalar potential. It's already there. Because if exponential is small, it is almost constant. Yeah. So this means Starobinsky model predicts plateau in a potential. This is what we really want. And we know also the reason for that, because the scale invariant, approximate scale invariance of the Starobinsky model at high curvature translates into the shift invariance of the scalar field, which is means plateau in the potential. So good. So theoretical point of view, very nice. But let us now go to observations. Oh, by the way, what is the meaning of m? If you expand this exponential in powers, you will see that the m is precisely the mass of the inflaton. It is 1/2 m squared phi squared. When you expand exponential, take quadratic terms. One is cancelled, and the next one will be quadratic. It will be just generate the mass term. Okay, now crucial point. Let us go to observation. So with the notation which I introduced before. So first, the amplitude of scalar perturbation was measured. This is it is just this number. So this number is what CMB tells us. On the other side, it can be calculated from the potential, and it can be, if you substitute the Starobinsky potential, we get this area, and the inflation corresponds to plateau when phi star is the order of Planck scale. So this means that this number fixes m. So m is again 10 to about 10 to 13 GeV. So we reproduce it. So fine. But now we have a model which has no free parameters. So we cannot adjust anything if it without adding anything. So now a crucial check comes. Crucial check says what are the values of ns and r this model predicts. You cannot adjust anything anymore because you have no free parameters. Okay, and what happens is if you just take ns, which is this is theoretical result, this is observational result, and we take this bound which I was talking about, Starobinsky gives this. You see the crucial difference. It reproduces Chebyshev-Mukhanov, but it gives you extra power of n. Extra powers of n, remember n is around 50-60, decreases tensor to scalar ratio by 1 order of magnitude. So you get this formula, you can exclude n, and you get this prediction. So this is the target of these 5 collaborations which are running now. Because if this confirms this, then Starobinsky is like Friedman, okay? If it is not confirmed, then sorry. If it is not serious, if it is confirmed closely, then some extra correlations like cube, quatic terms with curvature can, but if it will be order of magnitude different, then this will fail. So this is the main target of the observational cosmology today, in particular Japanese product and American product and so on. Good. So, yeah, oh, sorry, this I should put it at the beginning. This is just a definition of perturbations, scalar perturbations, tensor perturbation, 2-point function. Sorry, it should have happened before. Okay, so just as a bridge to my next lecture. So what maybe I should conclude at this moment. To conclude is that this is a really, that's why I think because of this, that Starobinsky model is in a poor position now. There are 300 models of inflation in the literature, 300 plus. So, but they all introduce some handmade stuff. And here you have a model which has no has no free parameters, nicely fits current observations, and has reasons for most fundamental physical features. That's why I consider it a number one, even though, of course, you know, some people may disagree. Okay, and this happens because of it has very nice theoretical background and also agrees with observations. That's why I think this. That's why not only I think, but it is a main target of the from the satellite cosmology. But now, in the remaining few minutes, I want to make a bridge to my last and third lecture tomorrow, because you may ask, where is dark matter? Okay, and perhaps what is the connection to the standard model? So I should put perhaps it in this way. Since this sounds very promising, we should try to build on this. This is very natural from the point of view of any series. You have something very good, try to build on. Yeah, it is not accidental, shouldn't be accidental. But the main point of Starobinsky inflation is gravitational origin of inflation. Yeah, even though when you write it in this way, this connection, this good for eyes of particle physicists, but the connection to the modified gravity is lost, because they just tell you the potential is this. But when you start, but when you find that this is actually comes just from this, from R squared, where we basically use only general covariance, okay, and go beyond Einstein and demand ghost freedom and scale invariance. This is tells you. This is, you can think about it as a gravitational origin of inflation, because this action delivers you simultaneously inflaton, which is, from this point of view, is a physical excitation of high derivative gravity. It gives you the reason for flatness of the potential. You exploit general covariance, and you exploit scale invariance of the R squared gravity. So, therefore, it is natural also to search for gravitational origin of dark matter. In addition, by using this framework. That's what I'm going to do tomorrow. Okay, and just to give a tip how it could be. Again, let us look at the. So this, for example, by the way, this is observed CMB spectrum in details. It's known as the Harrison-Zeldovich. But if you consider slow approximation, the formula for the power spectrum is this. And what is important of this formula is, you see here, this epsilon is a denominator. So for inflation, it has particular value, so you have a particular scale of perturbations. But what if I allow epsilon at smaller scales to be even smaller? If I allow it even smaller, this would mean peak in a power spectrum at lower scales. So what means peak in power spectrum? It means large perturbation. So if it is very large, then it can gravitationally collapse into the black hole. So this same framework allows for the, in principle, for the production of what's called primordial black holes. And tomorrow I will argue that these black holes can be dark matter. It's not particle dark matter. It is black hole dark matter. This will be the subject of my lecture tomorrow. Maybe last remark. So far, no connections with standard model, okay? So I will do just opposite to standard model. Standard model just, people say, oh, let's add some particle, it will be called dark matter. I'm not going to add any particle. I know the gravity is there, it can be strong enough to generate a peak. This peak can generate black holes, and these black holes can be dark matter. That's what I will be arguing tomorrow. So about the connection with the standard model is a much more tricky issue and non-trivial, but so far it is disconnected. Thank you. That's all.
So I want to start with a question about the fit with the data. So you said that the two predictions, you mean NS and R.
The key predictions, I would put it this way. This is the fit, because you have a free parameter M in the model, and you have the known amplitude of scalar perturbations. Yeah, you put it in and you fix M. So M is fixed, no free parameters. But then, by the way, the I and NS, they don't depend upon the scale. They have no dimension. But these are key issue, because both NS and R are observable. So once you have a model, you can calculate them. And the formulas are, you have this in terms of NS, and this cannot be easy, yeah? And the difference is the extra power of N here compared to Linde, which does the job, lowest R. So
the only parameter here.
And yeah, N in principle also absorb measurable, but there is no good formula for N, and it's very difficult to measure N. But you can exclude N. You have to take N from NS, put it here, you get this. So you can exclude N. So this is a precisionally known. So this gives you precision answer, sharp answer, what they should measure. 10 to minus 3. R is 10 to minus 3. So if they measure this R discover R in 10 to minus 3, they potentially can get 2 Nobel Prizes. One is the ultimate confirmation of inflation, because you just get R positive. And second confirmation, if this model, then this will be as standard as Einstein-Friedman. If not, as I said, then one has to look for something else. For the moment, I think this is the best proposal.
Another question then. So it's about your last comment, so about production of black holes.
Maybe probably better to talk about it tomorrow, because I have to develop. But I gave you the idea.
Small question.
Yeah, I gave you the idea.
Question about, so you say that, well, there might be a regime where epsilon is even smaller.
Yeah, it's called ultra slow. Yeah.
So this means that the earlier stage of the
after inflation.
After inflation.
So it means
so
after.
What controls this parameter? So what?
Well, you have to potential. You have to. No. For inflation, it's fixed. In Stravinsky, there is no such situation. We want to, by hand, produce peak in the power spectrum at lower scales by deforming the potential, or by adding extra terms to R squared, modifying F gravity function. 2 ways, but they're equivalent. So these are 2 pictures of the same physics. And I will do actually the second. I will modify Stravinsky to generate such peak. And it is a question whether it's possible in principle. I show you that it's possible. The idea is to generate at some scale epsilon very small. So within this framework, I can also include dark matter and this non-particle dark matter. This is, of course, even more speculative, yeah? But I just want to show you that it's possible. Okay, thank you. So tomorrow we will discuss it in more details. About this, I don't know how to answer this question in short, because this is an open issue, how to connect it with standard model. But we are doing it in the context of supergravity, supersymmetry. There it's possible.